Welcome to Chronicles of the Curious, where we explore the fascinating and mysterious aspects of science and nature. In this video, we will talk about some new experiments that are trying to crack one of the biggest questions in physics. What is dark energy? Dark energy is a mysterious substance that makes up about 68% of the energy density of the universe, and that causes the expansion of the universe to accelerate. However, we don't know what dark energy is, where it comes from, or how it works. Let's dive into this enigmatic topic and see what these new experiments are all about. Dark energy was discovered in 1998 by two teams of astronomers who were studying distant superstars. Expected that the expansion of the universe, which started with the Big Bang, would be slowing down over time due to the gravitational attraction of matter. However, they found that the expansion was speeding up, implying that there was some unknown force that was pushing the universe apart. This force was dubbed dark energy, and it was later confirmed by other observations, such as the cosmic microwave background radiation and the large-scale structure of galaxies. Dark energy is one of the biggest mysteries in physics, because it challenges our understanding of gravity and cosmology. According to Einstein's theory of general relativity, gravity is a manifestation of the curvature of spacetime, which depends on the distribution of matter and energy. However, dark energy seems to have a negative pressure, which means that it creates a repulsive gravity that counteracts the attractive gravity of matter. Moreover, dark energy seems to have a constant density, which means that it does not dilute as the universe expands, but rather dominates over matter as time goes on. There are many possible explanations for what dark energy is, but none of them are satisfactory or conclusive. Some of them are the cosmological constant. This is the simplest and most popular explanation, which assumes that dark energy is a constant property of space itself, or a vacuum energy that arises from quantum fluctuations. However, this explanation has a huge problem. The theoretical value of the cosmological constant is about 10 to the power of 120 times larger than the observed value, which is an enormous discrepancy that requires a fine-tuning or a cancellation mechanism. Quintessence. This is a more dynamic explanation, which assumes that dark energy is a scalar field that varies in space and time, and that has a potential energy that drives the acceleration of the universe. However, this explanation has many problems. It requires a very specific form of the potential energy to fit the observations, it introduces new degrees of freedom that may affect other physical phenomena, and it may violate some symmetries or conservation laws. Modified gravity. This is a more radical explanation, which assumes that dark energy is not a real substance, but rather an illusion caused by a modification or an extension of Einstein's theory of general relativity. However, this explanation has many challenges. It has to pass all the existing tests of gravity in the solar system and on Earth. It has to avoid instabilities or singularities in the equations, and it has to be consistent with other fundamental theories or principles. Therefore, dark energy is not well understood or explained by any existing theory or model, and it requires new experiments and observations to shed more light on its nature and origin. The new experiments that shed light on dark energy are designed to measure various aspects of dark energy and its effects on the expansion and the structure of the universe. Some of these experiments are ground-based, while others are space-based. Some of them are already operational, while others are planned or proposed for the near future. Some of them are DESI. This is the Dark Energy Spectroscopic Instrument, a ground-based experiment that uses a telescope in Arizona to map the three-dimensional distribution of millions of galaxies and quasars over a large volume of the universe. By measuring the positions and redshifts of these objects, DESI can probe how dark energy affects the growth of large-scale structures and the cosmic expansion over cosmic time. DESI started its scientific operations in 2021 and is expected to run for 5 years. Euclid. This is a space-based experiment that uses a telescope and a camera to survey the two-dimensional shapes and positions of billions of galaxies over a large area of the sky. By measuring the distortions and correlations of these shapes, Euclid can probe how dark energy affects the gravitational lensing and the clustering of galaxies over cosmic time. Euclid is planned to be launched in 2022 and is expected to run for 6 years. LSST. This is the Legacy Survey of Space and Time, a ground-based experiment that uses a telescope in Chile to take repeated images of the entire southern sky over a decade. By measuring the brightness and positions of billions of stars and galaxies, LSST can probe how dark energy affects the supernovae, the gravitational lensing, and the large-scale structure of the universe over cosmic time. LSST is planned to start its scientific operations in 2023 and is expected to run for 10 years. WFIRST. This is the Wide Field Infrared Survey Telescope, a space-based experiment that uses a telescope and a camera to survey the infrared sky with high resolution and sensitivity. By measuring the distances and shapes of millions of galaxies and supernovae, WFIRST can probe how dark energy affects the cosmic expansion, the gravitational lensing, and the large-scale structure of the universe over cosmic time. WFIRST is planned to be launched in 2025 and is expected to run for 6 years. These experiments are complementary to each other, as they use different techniques and cover different regions and epochs of the universe. Together, they will provide unprecedented information and constraints on dark energy and its properties. The expected outcomes of these experiments are to improve our knowledge and understanding of dark energy and its role in the evolution of the universe. By measuring various aspects of dark energy with high precision and accuracy, these experiments will be able to test different theories and models of dark energy, and to determine whether it is constant or dynamic, whether it is a substance or a modification of gravity, whether it has interactions or couplings with other fields or particles, and whether it has any relation or origin from quantum physics or cosmology. The challenges of these experiments are to overcome various sources of uncertainty and error that may affect their measurements and results. Some of these sources are systematic errors. These are errors that arise from imperfect instruments, methods, or assumptions that may bias or distort the measurements. For example, systematic errors may come from calibration errors, instrumental noise, atmospheric effects, astrophysical foregrounds, or modeling uncertainties. These errors have to be minimized and controlled by using robust techniques and cross-checks. Statistical errors. These are errors that arise from random fluctuations or variations that may affect the measurements. For example, statistical errors may come from sampling errors, measurement errors, cosmic variance, or shot noise. These errors have to be reduced and quantified by using large datasets and statistical methods. Theoretical errors. These are errors that arise from incomplete or inconsistent theories or models that may affect the interpretation and comparison of the results. For example, theoretical errors may come from missing or wrong ingredients, parameters, or predictions in the theories or models of dark energy. These errors must be identified and resolved by using physical principles and criteria. Therefore, these experiments must face and overcome many challenges in order to achieve their goals and to provide reliable and meaningful outcomes. We hope you enjoyed this video and learned something new about these new experiments that shed light on the origins of dark energy. If you liked this video, please give it a thumbs up and subscribe to our channel for more videos on science and nature. Also, let us know in the comments what other topics you would like us to cover in the future. Thank you for watching and stay curious.